Hello, ladies and gentlemen. You are welcome to this channel. Today, we shall be doing more examples on modeling with differential equation. As I used to say, whenever you want to model, there are 4 steps you need to follow. 1, you need to understand the physical law guiding the process. And secondly, you have to express the process mathematically. Then the third step is you have to solve the mathematics, and the final step is you have to interpret or apply the mathematics. So those are the 4 steps you need to follow. Let's look at an example here. This one involves modeling heating in building. Suppose that in winter, the daytime temperature in a certain office building is maintained at 70 degrees Fahrenheit. It's a good practice to sketch the process or the system. So this is the building. So the building is maintained at 70 degrees Fahrenheit on a normal day. The heating is shut off at 10 p.m. and turned on again at 6 a.m. That means the process is between 10 p.m. and 6 a.m. in the morning. So on a certain day, the temperature inside the building at 2 a.m. was found to be 65. So that means this is 10 p.m. 1, 11, 12, 1, 2, 3, 4, 5, 6. So at 2 p.m. inside the building, the temperature was found to be 65. And you remember the normal daytime when they close is 70 degrees Fahrenheit, when they close at 10 p.m. So now the outside temperature at that time, or on that particular day, the outside temperature is air outside. So was 50 degrees Fahrenheit at 10 p.m. So at 10 p.m. it was 50 degrees Fahrenheit, and that dropped to 40 F by 6 a.m. So at 6 a.m. the outside temperature had dropped to 40 degrees Fahrenheit. So what was the temperature inside the building when the heat was turned on at 6 a.m.? So they are looking for this temperature inside the building when it was turned on at 6 a.m. at the start of the building. Normally, when you visualize this, you realize that 70 degrees Fahrenheit at 10 p.m. when they close had dropped to 65. So it's expected that 6 a.m. the temperature will drop further. So to make use of our the stages of solution, what are the physical law, or what is the physical law guiding this process? So we are given information here that what experiments show that the time rate of change of the temperature T of a body B is proportional to the difference between the temperature and the temperature of the surrounding medium. So that means the time rate of change, TB is the temperature of this building, and TS is the temperature of the surrounding. So the time rate of change, TB with time, how it changes with time, is proportional to the difference between the TB, temperature of the building, by temperature of the surrounding. So that's just a physical law. So let's see it in a bigger picture. This is the picture. So 70 degrees Fahrenheit at 10 p.m. At 2 a.m. it has dropped to 25 degrees Fahrenheit, and at 6 a.m. we are looking for the temperature by our model. So the actual temperature 50 F by 10 and 40 F by in the morning. So we can find the average to be 45 degrees Fahrenheit. So that is 40 plus 50 divided by 2 will give us 45 degrees Fahrenheit. Secondly, we need to index this time range. At 10 p.m. that's the start of the time, that is the time 0. At 11, 1, 12, 2, 3, 4, 5, 6, 7, 8. So the 0 hour was at 10 p.m. and 8 hour is at 6 a.m. So let's take note of that. So to solve this, we start with the physical law. The TDT is proportional to TB minus TS. So we can rearrange this by proportionality. The T is equal to K TB minus TS. What is K? K is our proportionality constant. So sorry, this is TB, right? TB, change in TB with time. So now we can collect the like terms. The TB divided by TB minus TS is equal to K dt. So we can now integrate. That means T in ln TB minus TS equals to KT plus C. So we have two constants now, proportionality constant as well as the integration constant. So then let's take exponent of the two sides so that we can simplify the equation. Exponent of the two sides. So that will give us TB minus TS is equal to exponential KT plus C. So then we have TB minus TS is equal to, by indices, this is exponential KT multiplied by exponential C. And exponential C is all constant too. So it will be a bigger constant, exponential C exponential KT. So this has just simplified. You can find it separately. But we have just codified it to mean C star, which will mean a constant on its own too. So finally, our expression is TB is equal to TS plus C star exponential KT. So the first task is to find the first constant here and the second constant here. So how do we find it? You remember our TS from the information given, average temperature of the surroundings is 45. So our equation here can be TB is equal to 45 plus C star exponential KT. So what else shall we do here? We can now have, to get our C, let's use this condition at the start. So at time T is equal to 0, our temperature then was 70 degrees Fahrenheit. So that means at T is equal to 0, temperature of the building when time is T is equal to 0 is equal to 70. Therefore, we can just say 70 is equal to 45. So from this equation, right, equation 1 plus C star exponential 0. This is 0. Exponential 0 is equal to 1 because our T is equal to 0. Everything is 0 up here. So that means we have 70 equals to 45 plus C star. So that means our C star is equal to what? 25. 70 minus 45. So our expression now becomes what? TB equals to, that is equation 1 now becomes TB equals to 45 plus our C star exponential KT. So we have solved the C. We need to solve for K too. We need to solve for K. So how do we solve for K? Let's go back to the information. You can see this information is very useful because we sketch it very well. So at 2 a.m. there's another condition given to us that it was 65 degrees Fahrenheit. And at 2 a.m. the index hour there is 0, 1, 2, 3, 4. It was the 4th hour. So we can just say TB at T is equal to 4 is equal to 65 Fahrenheit. Therefore, we can now use it in equation 2 now. So it becomes TB equals to 45 plus 25 exponential KT. And our TB now is what? Our TB is 65. We can just put it directly there. So it means 65 is equal to this. So when we manipulate this, we are going to get K is equal to exponential KT. Exponential KT is equal to 65 minus 45 divided by 25, and that will give us 0.8, and that means our K is equal to minus 0.056. So we have gotten all our constant. So we can now substitute back into equation 1, and TB becomes what? 45 plus 25 exponential minus 0.056t. So that is our final expression. We have solved our model, and this is what we got. So the last stage is now to interpret or apply. You remember the question. What was the question? The question asked us to find T at 6 a.m. and that was what was stated here. What was the temperature inside the building when the heat was turned on at 6 a.m.? So at 6 a.m., what was the time index then? That will be our 8 hour. Our 8 hour. So that means at 6 a.m. T is equal to 8. Therefore, our TB then is equal to 45 plus 25 exponential minus 0.056 times 8. And if you evaluate that, that is going to give us TB, temperature of the building, is equal to 61 Fahrenheit. So that is the solution to the question. And you can see it is very reasonable. So this is 70 degree Fahrenheit at 10 p.m. when the company closes or the building shuts down. And at 2 a.m. it has dropped by 5 degree Fahrenheit to 65. And here it is now 61 degree Fahrenheit. So thank you for listening. Please hit at the subscribe button there and drop any comment if you have any question. Thank you.